Awesome. Well, thank you very much for the introduction and for giving me the opportunity to give this talk. Again, my name is Gao Samaphon Tinyanon. I'm a postdoc at UC Santa Cruz. And I'm super excited today to tell you about this mysterious supernova called 2020 WNT. And hopefully it will serve as a reminder why finding out and following up on good old supernovae is still an exciting science. So first of all, let me introduce you to some generic properties of supernovae. So here I'm showing you a collection of like just an average light curve of 3 different types of supernovae. Up here, the brightest one here I have on here are type 1a supernovae, which come from explosions of white dwarfs. Unfortunately, I don't get to talk about these guys today. These two, a little bit less fainter lines are from core collapse supernovae. So these are death of massive stars. The yellow line here represents the type 2 supernovae. These are supernovae that explode with most, if not all, of the massive hydrogen envelope intact around the progenitor star. And as a result, you see this plateau in the luminosity light curve from the recombination of the hydrogen envelope. If this hydrogen envelope is removed somehow from the progenitor star prior to the explosion, you get a strip envelope supernovae or type 1bc supernovae shown here. For these explosions, you notice that all the tail, the decline rate are quite similar, and that's because these explosions are powered by radioactive decays. So now in the past 10 to 15 years, we have started to use these untargeted wide field all sky surveys to search for transient instead of using galaxy targeted observations. And as a result, we have been reviewing and finding out about all these different types of rare, weird, odd transients that we did not know before. And one of those peculiar transients are called superluminous supernovae. These are death of massive stars that somehow manage to get extremely luminous. And with a luminosity increase of a factor of 100 to 1,000 over a typical core collapse supernovae, the evolutionary timescale of these explosions are typically quite a bit longer than normal supernovae as well. Superluminous supernovae also come in 2 flavors, type 1 with no hydrogen and type 2 with hydrogen. Today, I will only be talking about type 1, superluminous supernovae with no hydrogen. So how do you get this huge boost in luminosity in these events? So first of all, when you think about radioactive decay, you might think, well, if you need more luminosity, you can just increase more radioactive material. So let's see how this would work, right? So in this scenario, if you boost the amount of nickel that you produce in the explosion, then as a result, you would get higher peak luminosity. Great. The problem here is that the rise time of the transient is also set by the total mass that you have in the ejector, because more mass that you have, it takes longer for the light to diffuse out. And this presents a problem for most superluminous supernovae. When we try to fit the light curve of these events using a radioactive decay model, what you find is that you need more mass in nickel than you have in ejector mass. So for example, from the rise time, you might get an ejector mass of about 10 solar masses, but from the peak luminosity, you might need 11 solar masses of nickel, and that is not physical. And with this being the case for most superluminous supernovae, you need some extra source of luminosity. One of the most simple and successful models to explain behavior of superluminous supernovae are magnetar models. So in these models, you assume that the neutron star that is born in the core collapse is highly magnetized and is spinning really, really rapidly. And this magnetar is somehow coupled to the ejector and is spinning down via dipole radiation, depositing this energy into the ejector. In this model, the spectroscopic imprints are quite clear. You get blue continuum and a series of absorption from ionized oxygen because of this very energetic source of energy in the middle of your ejector. So that's one way. Another way that we can explain the evolution of these superluminous supernovae is by having some circumstellar medium interaction. So in this scenario, the progenitor star loses some mass before its death, and then the resulting supernova shock wave crash into these CSM, producing extra light. These models are particularly good at explaining bumpy light curves that are not just a smooth evolution. And they also have their own very clear spectroscopic imprints, which are these narrow spectrum lines that you get from ionized but slowly moving circumstellar mediums. For the population of superluminous supernovae that we have observed, the Magnetar models work really, really well. So this is a collection of MOSFET fits from Nichols et al. 2021, showing your favorite superluminous supernovae that are very well observed with a lot of data. And these are the Magnetar model fit to these data, just to try to convince you that this works quite well. So let's switch to our protagonist of the story, supernova 2020 WNT. So 2020 WNT got discovered on October 14, 2020 by CTF. And here I'm showing a detection stamp from CTF on the left three panels. You get the new image, the reference, and then the subtraction showing the detection of the supernova. And then on the right here, I'm just showing the false color image of the supernova at peak. And you can see that it's much brighter than the small little host galaxy. About a month after the first detection, we went and finally got the spectrum of this supernova. And from here, you can see that there's no hydrogen and no helium. So at first we thought, okay, another type 1c supernova. I also have beautiful HFC images here of the host galaxy with the supernova location here. We can take more look at it later. But what makes this supernova super exciting is that after we got that first spectrum, the light curve, so the first spectrum is here, notated by this black line. The light curve continues to rise and rise and rise and rise. And it took in total about 70 days for the supernova from the explosion to its peak. So this is extremely long for a normal type 1c supernova, which usually only rise on a matter of a few days, and the longest is maybe a week or two. And the peak luminosity of this event is also really high at almost -21. So this is getting it close to this population of superluminous supernova that I'm showing here. So in comparison, most of these different lines are from other superluminous supernovae in the literature. And here I'm showing a typical normal strip envelope type 1c supernova here, 07GR, already shifted up by 1.5 magnitude. So you can see what kind of difference in luminosity that we have here. So now, there's a problem with this light curve, however. So we try to fit this light curve with a Magnetar model because we think, you know, it's the best one for other for other superluminous supernovae. And we have some problems. First of all, the rise time, we just really couldn't get the rise time to fit the data very well in order to get to this peak luminosity. And secondly, there is this very sharp knee in the light curve. This is more pronounced in the photometry rather than the bolometric luminosity, but there's a really clear knee here that the Magnetar model just cannot fit very well. And the reason is because for these Magnetar models, the essential assumption is that the diffusion timescale in the ejecta of these superluminous supernovae have to be on the same order of magnitude as the energy injection timescale. And this is simply to allow for the Magnetar to really power that very luminous curve. If the diffusion timescale is much longer than the large luminosity coming in from the magnetar needs too much time to diffuse out, and the resulting transient will not be as bright at peak. So because of that assumption, we just cannot get this long rise in the light curve to match. Another problem is that when we take a look at the spectra, as a reminder, the first spectrum we have looks like a normal 1C. So we keep getting the spectrum of this event. And I'm showing here 20 WNT is in this red line, 07GR, the normal 1C is down here. And up here, I'm showing samples of superluminous supernovae. And you can see that the spectroscopic imprints of the magnetar that I mentioned, the blue continuum, the oxygen to absorptions, 2020 WNT didn't have any of that. And this is also true all the way from before peak to through peak and also after peak. So from here, we concluded that the spectroscopically 20 WNT looks more like a normal 1C than a superluminous supernova. But when we wait long enough at late time, this is a nebula spectrum of 20 WNT. It's now starting to look like a superluminous supernova. So here, 20 WNT is shown in red. I have like a mean spectrum of type 1C down here and a superluminous spectrum at late time up here. So you can see that 20 WNT have kind of this transition from a 1C-like to a superluminous-like at late time. And we'll talk more in a little bit of what we think is happening and why it's having this behavior. So Gemini comes in here because we got some fast turnaround time to observe this supernova in the near infrared to complement our data from the optical. So the first G-near spectrum that we got was from about 81 days post-peak, which shows all these rich spectroscopic features in the near infrared that we didn't get in the optical. And after that, we thought, okay, maybe it will fade and get too faint for another epoch of spectroscopy. So after the supernova went behind the sun, came back, we got another epoch of near-infrared observation, this time just the photometry from IRTF specs. And we started to see this like really red color in the near-infrared bands. So we went back and asked for another epoch of Gemini observations, and we ended up getting both NIRI imaging and G-near spectrum at this late time. And what these observations really showed us is that there is some dust and carbon monoxide getting formed in the ejecta of this supernova, which is extremely exciting for a context for superluminous supernovae. There has been only one detection of dust formation, and there have never been any sign of carbon monoxide formation at all. And this is mostly because most superluminous supernovae are too far away, so that this CO feature in the K band get redshifted out of the near infrared band that we can see from the ground. So this is a super exciting observation for us. Another thing that we are able to do with this late time spectrum is that we are able to try to fit it with some nebula model. This one is from Under Yerkstrand 2017, and this allows us to put a further constraint on the ejecta configuration of this supernova. If you have more time, you can ask me about this, how this modeling is done. So if you don't think that the magnetar contributes to the power of the supernova at peak, then what else can it be? So we considered a few different radioactivity models. First one of all, of course, we have a long-lived supernova. We all want it to be a parent-stability supernova, which is this theorized explosion of extremely massive stars. And so, of course, that's the first model we check if we have a match. And the unfortunate part is that the rise time and the peak magnitude of this supernova don't match the classical parent-stability models very well. But we are able to fit it much better with just a more simple radioactive decay model. And the conclusion that we get is that This supernova can be explained by about 5.6 solar masses of nickel and 46 solar masses of total ejecta. So in this case, it's about 10% of the ejecta in nickel 56, which is a lot, but not completely unphysical. And so yeah, that's the conclusion for this supernova. The magnetar may be there. From the nebula spectrum, we see some signs that it looks somewhat like some superluminous supernovae, but we know that it doesn't power the peak based on other observations. We also found that strong CSM interactions are not likely because we don't see any narrow lines, no radio detections. So we think that it's a radioactive, actively powered supernova with about 5 to 6 solar mass of nickel, and the process that create this supernova is still quite an open question. So I will leave you with a summary with this pretty picture, and we'll take any questions. Thank you.
Thank you very much, Carl. That's great talk and that's beautiful data. So are there any questions in the room or online? Please.
Can you hear me? Okay, great talk. I have two questions. I was wondering if you could derive some constraints from the, I think you're seeing the tail of the cooling envelope emission. So can you derive some constraints from that part of the light curve?
This part?
Yes, exactly.
Yeah, thank you for asking that. So that tail is real. It came, we checked the CTF data and Atlas. They all show this brief cooling phase. The best model to explain this kind of behavior is just, as you said, shock cooling in some extended envelope. We try to use Tony Perot, like 2015 or 2021 model to derive some constraint on the envelope mass and size, but we still couldn't get the color to work quite right. But so yeah, essentially we have data from R band and G band, and fitting those two bands separately give a very different answers. So yeah, that's one thing we're still working on. It's one of the few loose threads of this data set.
I see, thanks. And another question is, in your conclusion, you said that CSM interaction is unlikely, but I was wondering, because we do observe like some supernovae where they likely are powered by CSM interaction, but the signature is hidden. Can that be a possibility?
Yeah, so we did definitely consider that possibility, and especially interactions with hydrogen poor CSM can be relatively easy to hide compared to hydrogen rich CSM, because the lines that you would create are quite a lot fainter. The issues with hidden CSM scenario is that usually, as the supernova expands and cool, you typically reveal the features of CSM interactions at some point. But here we have spectra from, have this plot here that shows epochs that we have spectra up here. So we sampled this thing, throughout the peak, and also very well on the tail. And at none of these epochs we see any narrow emissions at all. And in addition, we also have some radio observations that didn't produce any detection, but we are still working on that to convert it to a constraint on the CSM density.
I see. Thank you. This is awesome.
Thank you.
Question from Janice.
Hi, great talk. So what is the range of masses of the progenitor star?
That is definitely something I have to look up and work on. But yeah, if it's a single star, then it must be, in 100 solar masses range to have this much ejecta mass. And binary models are possible as well. Another thing I should mention is that this the mass number that we get from fitting the light curve shape depends quite strongly on the opacity that we assume. So if the ejector has higher opacity, then this total ejector mass can come down quite a bit.
So the context of the question is I work on massive star formation, so I'm interested. I'm not sure you can answer this, but I'm interested in the upper part of the stellar initial mass function, and I'm wondering whether or not what you see in superluminous supernovae are consistent with what we expect from a normal IMF.
Right. You mean in terms of rate of these events?
Yes, in terms of rate, exactly. Yeah.
Yeah, that is definitely not my area of expertise, but I believe that the general numbers are consistent with superluminous supernovae coming from the very, very massive star. I believe the rate is about like 0.1% of all core collapse supernovae are superluminous. But yeah, this connection between massive star population and the supernovae that we see is definitely some something that we are all working hard on, because even for a normal core collapse supernovae type, normal type 2 supernovae that we know for a fact come from red supergiants, there's still a lot of open questions on whether or not there's an upper limit on the mass of red supergiant that would explode as a type 2 supernova. So yeah.
Thank you, Cal. We don't have any questions online. For the sake of time, we'll move on to the next talk. Thank you again. Let's thank Cal.
Thank you so much.